Fibonacci sequence is one of the most famous series of numbers. It was famously proposed by an Italian mathematician named Fibonacci. He is also known to be the most talented Western mathematician during the medieval times. Well, it's really easy to understand how this recursion works. Consider an initial sequence of 0 and 1. The next number in the sequence is obtained by adding the previous two terms. For example, here it's 0 plus 1, which is just 1. And for the next term, we do the same, 1 plus 1, which is 2, and so on. In this video, we are going to be solving for the nth term in Fibonacci sequence using an infinite power series. Let's represent f sub n to be the nth Fibonacci number, then we have ourselves a recursion as follows. We need a way to obtain the nth term in the sequence, and to do that, we can make use of generating functions. But what are generating functions? Let's say we have a sequence of numbers a sub 0, a sub 1, and so on. We can make an infinite power series using the numbers from the sequence a_n's as the coefficients, and that's what we call a generating function. So what's the setup then? Let us consider the generating function capital F of x, where the coefficients are numbers from Fibonacci sequence, that is f sub n. But as we know, the recursive definition for n greater than or equals 1, we can rewrite f2 as f0 plus f1, and f3 as f1 plus f2, and so on. The first terms from each bracket can be grouped together, and the same goes for the second terms from each bracket. And the grouping is done so that we can shape our capital F of x back. And after plugging in for f sub 0 equals 0 and f sub 1 equals 1, we get our expression for capital F of x. We can now factorize the binomial 1 minus x squared into 1 minus x times alpha plus times 1 minus x alpha minus, where alpha sub plus or minus equals 1 plus or minus the square root of phi over 2. Later, we do some partial fractions, and then finally, we can write 1 over 1 minus x as the famous geometric power series. And the coefficients of this power series must match the ones from our initial definition of this generating function, having f sub n as coefficients, so we know they're equal to each other. And that brings us to the famous Binet's formula. Let us verify if it really works and plug n equals 3. Yep, it works. Now, if we wanted higher terms like the millionth or a billionth term in Fibonacci sequence, we can approximate the formula where only the 1 plus square root of phi over 2 remains because the other one lies between minus 1 and 1. So as n grows, that term does not contribute much. Now, if we observe using this approximation we have, the series grows incredibly fast. The 50th Fibonacci number is already over a billion. And here are some higher values. If you also observe by taking the ratio of every two consecutive terms from the Fibonacci sequence, it seems to approach a number. Well, if we use the Binet's formula, we can calculate this constant as limit n tends to infinity, f sub n plus 1 over f sub n. And that is, 1 plus square root of 5 over 2, which is about 1.618, and it's famously called the golden ratio, represented by phi. It's pretty cool because its golden rectangle representation appears a lot in nature, having familiar complex patterns. If you've learned something through this video, be sure to subscribe for more such content, and till then, you can watch these fascinating math videos on the screen.